Welcome back, everyone, to the deep dive. Today we're going to be diving into something a little different.
Oh,
Yeah, it's,
different how?
well, you know how we usually get, like, articles and blog posts and things like that. Well, this time, one of our listeners actually sent us a PDF.
Wow, a whole PDF. What's it about?
Yeah, it's called Counting.pdf, and it's by Andreas Klappendecker. It's all about, the math behind counting. And, like, not just, like, one, two, three, but, like, the really clever strategies that mathematicians use for more complex counting problems.
Oh,
Like, how many possible license plates can there be in a certain state? Or how many different strong passwords could you create? Things like that.
that's pretty cool. I mean, everyone counts every day, but I've never thought about it like from a strategic standpoint like that.
Yeah, and, it turns out there's all sorts of, like, kind of counterintuitive concepts involved. Like, have you ever heard of the pigeonhole principle?
I can't say that I have.
Well, get this. The pigeonhole principle basically says that, like, if you have more pigeons than pigeonholes, at least one of those pigeonholes has to have more than one pigeon in it.
Sounds pretty straightforward.
It does, but you can actually use it to prove some pretty surprising things. I promise we'll get to that later on. But first, I think we need to kind of set the stage, get the basics down. So what do you say that we start with some fundamental counting principles?
Yeah, let's lay that foundation.
Awesome. So where do we begin?
Well, the building blocks of counting are the product rule and the sum rule.
Okay.
And actually, they're both way simpler than they sound. Let's start with the product rule.
Right, product rule.
So imagine you're getting dressed in the morning. You have to choose a shirt, A and D. You have to choose a pair of pants to wear.
Right.
So let's say you have 5 shirts and you have 3 pairs of pants.
Okay. I see where this is going.
The product rule basically says that you have 5 times 3 or 15 different outfit combinations.
Right. So each choice you make kind of multiplies the possibilities.
Exactly.
Okay, that makes sense. But what about when we have options? Like if we're trying to decide between a burger or a pizza?
That is where the sum rule comes in.
Sum rule.
So if you have 5 different burgers to choose from and 3 different pizza options, then you have 5 plus 3
Right.
or 8 total choices.
Got it. So product rule for and sequential tasks.
Right.
And sum rule for or when you have to make a choice between options.
Yeah, you got it.
Okay. So far it seems pretty straightforward, but I have a feeling it gets more complex than this. Like, how do these rules apply to something like counting functions? The source material mentions those.
Yeah, so for regular functions where you have, n choices for each element in the first set, and then you have m elements in the first set, it would basically just be n times itself in time.
So like n to the power of m.
Right, exactly.
Okay, so essentially the product rule helps us figure out how many ways we can pair up elements from those two different sets.
Yeah.
Okay, that makes sense. What about injective functions?
Injective functions?
Yeah.
They have a constraint, so basically you can't repeat elements in the second set.
Ah.
So like if the first set is larger than the second set, you can't have an injective function.
Right. There wouldn't be enough unique elements in the second set to pair with all the elements in the first set.
That's right.
Got it. But if the first set is smaller or the same size as the second set,
Okay.
you basically just need to make sure you don't map any two elements to the same destination.
Right. So we have to be careful not to double book any of our elements.
Yeah, exactly. So you start with n choices for your first element, and then you only have n minus 1 for your second element.
Because you've already used one up.
Exactly.
So it's like a chain of decreasing choices until every element in the first set has a unique partner in the second set.
Right.
Okay. I can see how this could get pretty tricky pretty quickly. The source material also mentions something called the subtraction rule.
The subtraction rule.
Yeah. And something called the principle of inclusion and exclusion. Okay.
These sound a little intimidating. What are those all about?
No, they're not as scary as they sound. The subtraction rule is basically just a way to avoid overcounting.
Okay.
So, for example, let's say we wanted to count all the bit strings that start with a 10 OR and with a 0. We can't just add the number of bit strings that start with a 1.
Right, because some of those bit strings would satisfy both conditions.
Exactly.
So we'd be counting them twice.
Yeah, so we have to subtract the number of bit strings that start with a 1A and D and with a 0.
Okay, so it's all about being careful and making sure we're not counting any elements more than once.
Yeah. And then the principle of inclusion and exclusion is basically just an extension of that idea. It handles overlaps between more than 2 groups.
Okay, so if we had 3 or 4 different conditions we were looking at,
Yeah.
it's like a way to systematically add and subtract and make sure we're only counting each element once.
Yeah, exactly. It's all about organizing information carefully so you don't have any duplicates.
Got it. And speaking of clever organization, let's finally talk about that pigeonhole principle we mentioned earlier.
Oh, yeah. You ready for this?
Yes, bring on the pigeons.
So basically, the pigeonhole principle says that if you have more pigeons than pigeonholes,
Uh-huh.
at least one pigeonhole has to have more than one pigeon in it.
Right.
So
I mean, it's pretty straightforward when you think about it like that.
it is, but it's pretty powerful for proving some surprising things.
Yeah. That's what I'm really curious about. Like, how does something so simple lead to those surprising results? I know the source material mentions something about birthdays. Can you explain that?
Yeah, so imagine you have a group of 174 people,
Okay, 174 people.
and you want to know the chances of at least 2 people in that group sharing the same birthday.
Okay.
Turns out there's a really high chance of that happening.
Really? That seems counterintuitive. There are 365 days in a year. You'd think you'd need way more people to guarantee a shared birthday.
Well, that's where the pigeonhole principle comes in. Our pigeons are the people, and the pigeonholes are the days of the year.
Ah, okay.
Since we have more people than possible birthdays,
Right.
at least one of those birthdays has to be shared.
Wow. So it's not really about, like, the exact number of people who are sharing a birthday, but the fact that we know for certain that at least 2 people do.
Exactly. It's all about proving that something exists even if we can't say exactly what it is.
That's pretty cool.
It is, and there's actually a generalized version of the pigeonhole principle. It states that if n objects are placed into k boxes, then at least one box has to have at least the ceiling of n divided by k objects.
Okay. That's a little more abstract. Can you give me a concrete example? The source mentions something about points in a square.
Absolutely. So imagine a unit square. So a square with sides of length 1.
Okay. Got
And let's say we have 10 points inside that square.
Like 10 points.
The pigeonhole principle guarantees that at least 2 of those points will be
bad.
closer than 0.48 units apart.
Wait, how do pigeons and squares relate to each other? This is starting to sound like magic.
No magic here, just clever logic.
Okay.
The proof involves dividing that unit square into 9 smaller squares.
All right. 9 smaller squares.
Since we have 10 points and only 9 squares, at least one square must contain 2 points.
Right.
And then using a little bit of geometry, we can actually show that the maximum distance between those 2 points in that smaller square has to be less than 0.48 units.
Okay, wow. That's a really creative application of the pigeonhole principle.
Mm-hmm.
I'm starting to see that it could be used in all sorts of unexpected ways.
Yeah. And you know what? Now that we've laid that groundwork with those basic counting principles and the pigeonhole principle, I think we're ready to move on to some other essential counting tools.
Okay.
Permutations and combinations.
Okay, permutations and combinations. Oh, I remember learning about those in high school math class, but a refresher would be great.
For sure. So a permutation is basically just an ordered arrangement of objects. Like, think about arranging books on a shelf. The order you put those books on the shelf matters.
Right. So ABC is different from CBA, even
Yeah.
though we're using the same letters.
Exactly.
Okay, so permutations are all about order. What about combinations?
So a combination is basically a selection of objects where the order doesn't matter.
Okay.
So think of it like choosing toppings for a pizza. It doesn't matter if you choose pepperoni then mushrooms or mushrooms then pepperoni. You end up with the same pizza.
Got it. So permutations are all about order, and combinations are about selection. I'm guessing there are some formulas for calculating these. High school math is a bit hazy for me now.
There are, but really the logic behind them is more important than memorizing the formulas themselves.
Okay.
So for permutations, we're essentially multiplying the number of choices we have at each step.
Okay.
So if we're trying to arrange 3 letters like A, B, C,
Okay.
we have 3 choices for the first spot,
Uh-huh.
2 choices for the second,
Okay.
and then only 1 choice left for the last spot.
Right. That's 3 times 2 times 1.
Exactly, and that's 3 factorial.
Factorials.
Mhm.
I vaguely remember those.
Yeah.
Okay, so it's like a chain reaction of multiplication.
Mm-hmm.
What about combinations? Why do we divide by poenum or factorial?
Yeah.
The source material has a formula that does that.
Yeah. We divide to basically correct for overcounting when the order of things doesn't matter.
Yeah.
So let's say we're choosing 2 letters out of ABC.
Right.
We could have AB, AC, or BC.
Right.
But as a combination,
Uh-huh.
all of those are actually the same.
Yeah. We've chosen a group of 2.
Exactly. So dividing by 2 factorial eliminates those duplicates.
Right. We're basically saying, hey, those arrangements are all the same in the eyes of a combination.
Yeah. And these permutations and combinations, they pop up all over the place.
I bet.
From forming committees to designing experiments, analyzing data, and of course those poker hands that you mentioned earlier.
Right. Poker hands are definitely all about combinations. The order you get the cards doesn't matter, just the final hand you're holding.
Exactly. You're dealing with a combination of 5 cards from a deck of 52.
And that formula helps us calculate just how many possible hands there are.
Right.
Okay, so this is all really interesting.
Before we move on to even fancier counting tricks,
Okay.
I wanted to touch upon something called the binomial theorem.
Binomial theorem.
Exactly. The source material mentions it in connection to Pascal's triangle.
Pascal's triangle. Now, that I remember. That was one of those things in math class that just looked really cool, that triangle of numbers.
Yeah.
How does that relate to the binomial theorem?
So the binomial theorem is all about expanding expressions, like x plus y raised to some power.
Okay.
And Pascal's triangle, with its rows of numbers, magically reveals the coefficients in those expansions.
Wait, so a simple triangle can help us expand those complex algebraic expressions?
It can. Each row in Pascal's triangle corresponds to the coefficients in the expansion of x plus y raised to a specific power.
Wow. I love when math gets visual.
Yeah, it's a really beautiful example of how a visual pattern can actually, encode deep mathematical relationships.
That's amazing. The source also mentions something called Vandermon's identity.
Vandermon's identity.
Yeah, which sounds even more mysterious. What is that one all about?
Vandermon's identity is a bit more advanced, but it essentially deals with choosing objects from 2 different sets.
Okay.
So, imagine you have a box of red balls and a box of blue balls.
Okay.
And you want to figure out how many ways you can choose a certain number of balls in total, taking some from each box.
Okay. My brain's starting to feel a bit full. This is a lot to take in, but it's all incredibly fascinating. I'm starting to see how these counting tools are more than just abstract concepts.
Right.
They have real-world applications.
Absolutely.
Okay, I think I'm ready for a little mental break, but I'm excited to see where this deep dive takes us next.
Yeah.
This is cool stuff.
It is. Welcome back. Ready for some more counting fun?
You bet.
Mm.
I'm excited to see what other counting tricks we can uncover. Last time we left off talking about permutations and combinations,
Right.
where all the objects were unique. But in the real world,
Yeah,
things aren't always that neat and tidy.
exactly.
What happens when we have to account for repetition?
So when we allow repetition, we enter the world of multisets.
Multisets.
These are like sets, but elements can actually appear more than once.
So it's like having a bag of marbles, but some of the marbles are identical twins.
Yes, exactly.
How does that change how we count?
It definitely adds a layer of complexity. Think about choosing scoops of ice cream.
Okay, that's great.
You might want 2 scoops of chocolate and 1 scoop of strawberry.
Oh, yeah.
That's where combinations with repetition come in.
I see where you're going with this.
Yeah.
So in a regular combination, we could only pick each flavor once.
Right.
But with repetition, we can have multiple scoops of our favorites.
Exactly. And there's a really clever formula for calculating these combinations with repetition. And it turns out it's the same as the number of ways to choose objects from a larger set without repetition.
Wait, really? So adding repetition makes it equivalent to choosing from a bigger set without repetition? My brain hurts.
It's a little counterintuitive.
It is.
But there's a really cool visual representation that helps explain why this works.
Okay, I'm all about visuals.
Called stars and bar.
Stars and bars.
So imagine we're representing our ice cream choices with stars. So 2 stars for chocolate.
2-star chocolate?
1 star for strawberry.
Okay, 3 stars total. I'm picturing it. What about the bars?
The bars act as dividers between the flavors, so
Okay.
we need 2 bars to separate our 3 scoops.
Right, so we have 3 stars and 2 bars,
Yeah.
which is a total of 5 elements to arrange.
Right.
So we're essentially figuring out how many different ways we could arrange those 5 elements to represent our ice cream choices.
Exactly. And it turns out the number of ways to arrange those elements is the same as choosing 2 objects from a set of 5. And choosing 2 objects from a set of 5 is a combination without repetition.
Yeah.
So we've cleverly transformed our repetition problem into a form that's easier to handle.
That is really clever. It's amazing how a visual representation can make a complex concept so much clearer. Okay, what about permutations with repetition? Are those as tricky?
Permutations with repetition are surprisingly straightforward. So let's say we have 4 flavors of ice cream and we want to create a 3-scoop cone.
Okay, yummy.
We have 4 choices for each scoop,
Uh-huh.
and we're making 3 choices.
Right.
So it's simply 4 to the power of 3,
Okay.
or 64 possible permutations.
Wow. That's a lot easier than dealing with those factorials we saw with regular permutations. It seems like repetition can actually simplify things in some cases.
Yeah.
Yeah.
And you know what? Let's switch gears a bit
Okay.
and talk about another scenario. Permutations with indistinguishable objects.
Indistinguishable objects, okay.
So imagine you have a bag of marbles, but some of the marbles are identical, like you can't tell them apart.
Okay, so this is different from repetition. We're not dealing with multiple copies of the same object, but rather objects that look exactly alike.
Yeah.
How do we handle that when we're counting permutations?
We have to adjust our counting to account for the fact that swapping two identical objects doesn't actually create a new permutation.
Right.
So it's like rearranging the letters in the word success. Swapping the two S's doesn't actually give you a different arrangement.
That makes sense. It's like those identical marble twins we were talking about before. Switching their positions doesn't actually change the overall arrangement.
Exactly.
So how do we factor that into our calculations?
Well, the formula involves dividing the total number of permutations as if all the objects were unique.
Okay.
By the factorials of the number of each type of object.
So we're correcting for overcounting.
Exactly.
Can you walk me through an example? Let's say we have 3 red marbles, 2 blue marbles, and 1 green marble.
Okay.
How would we calculate the number of distinct permutations?
So we'd start by calculating 6 factorials as if all 6 marbles were unique.
Okay.
And then we divide by 3 factorials for the red marbles, 2 factorials for the blue marbles, and 1 factorial for the green marble.
So we're essentially pretending that all the marbles are unique at first.
Yeah.
And then scaling back down to adjust for the indistinguishable groups.
You got it.
It's like fine-tuning our counting lens to see those subtle differences.
Yeah, and you know what? All of these counting techniques that we've been talking about, from basic principles to repetitions to indistinguishable objects, they're actually incredibly valuable tools in so many different fields.
I bet.
You know, they help us analyze data, solve problems, make informed decisions.
Yeah, we already talked about how they can be applied to password rules and poker hands.
Right.
What are some other real-world applications for these counting techniques?
Well, they're really foundational in probability and statistics, like calculating the odds of winning the lottery that involves combinations. And then in computer science, analyzing algorithms. Designing efficient data structures often relies heavily on these counting techniques. And even in everyday life, understanding these principles can help us make more informed decisions.
So it's not just about counting marbles and arranging letters.
No.
It's about understanding those fundamental ways that we can group and order and select objects. And that has implications in countless fields.
Yeah.
Wow. This has been a truly eye-opening deep dive. I'm starting to appreciate the power of counting in a whole new way. Wow, we've covered some serious ground in this deep dive.
We have.
From those basic counting principles to permutations and combinations, and even those tricky situations with repetitions and indistinguishable objects, it's amazing how these seemingly simple concepts can unlock such complex problems.
It is. It's really fascinating how they can be applied to so many things.
Yeah.
Like analyzing patterns and predicting things. And the more you practice using them, the more intuitive they become.
That's true. It's all about recognizing the right tool for the job. We've talked about how these techniques apply to password security. Poker hands, even things like lottery odds and algorithm analysis.
It's incredible how applicable these principles are.
It really is.
You know, it really just speaks to the power of mathematics as a framework for understanding the world around us. Counting isn't just about numbers. It's about logical thinking. Strategic problem solving and recognizing underlying patterns.
Totally. It's been so much fun exploring all of this with you.
Yeah.
But before we wrap up,
I
have a question that's been bugging me.
Okay.
We talked about how to count the number of possible license plates. But what if we wanted to count the number of license plates that are palindromes?
Palindromes.
You know, those plates that read the same backward and forward.
Oh, yeah. That's a great question. Yeah. And it's a perfect example of how we can use all those counting techniques we've learned to solve an even more specific problem. So to count palindromic license plates, we'd have to think carefully about the structure of a palindrome. Since the first half dictates the second half, we really only need to figure out how many ways we can create the first half.
So we're essentially cutting the problem in half. So if a license plate has 6 characters, we only need to worry about the first 3.
Exactly. We could use the product rule to calculate the number of ways to choose those first 3 characters. You know, taking into account whether they can be letters or numbers. And then the rest of the characters are just determined by the first three.
To create that palindromic pattern.
Exactly.
That is so clever.
Yeah.
I'm starting to see how these counting techniques can be like building blocks.
Yeah.
You know, we can combine them in all sorts of ways to solve new challenges.
It's really cool. It's
Yeah.
like the more you explore,
The more connections you find.
well, I am definitely inspired to keep counting. This deep dive has been an incredible journey.
It has.
And I'm sure all of our listeners have gained a whole new appreciation for the power of counting.
For sure.
And to all of you amazing listeners out there, keep those brains buzzing.
Yeah.
You never know when you might need to calculate a permutation or apply the pigeonhole principle or even figure out how many palindromic license plates are out there.
Happy counting, everyone.
And that's a wrap on another deep dive. Catch you on the flip side, knowledge seekers.